I'm Joel Sercel, CEO and founder of Transastra and PI of this NIAC Phase 2 study, LPMO, or Lunar Polar Mining Outpost. I'd like to thank NIAC for funding this exciting effort and our collaborators and contributors, including the Transastra engineering team and the investors who have provided funding to augment this work, as well as our co-Is and collaborators. This study seeks to solve the problem of building a cost-effective and growing lunar outpost that harvests water to be used in making rocket propellant using two potentially breakthrough innovations, the Sunflower Power Tower and RGD, or radiant gas dynamic mining. The concept of the Sunflower is to place lightweight solar reflectors on deployable towers in or near PSRs to bring solar power to large surface-level solar arrays, all in a single landed package. The concept of RGD mining is to integrate multi-frequency subsurface heating modalities into mobile rovers we call beetles that can harvest water by sublimation and cryo-trapping without the need for excavation. During phase 1 of this effort and in year 1 of this 2-year study, we have shown that these inventions, if they can be matured to flight readiness, can enable a dynamic and exciting lunar outpost that can grow from a small scientific outpost to a large research station, and then to a commercial enterprise that can comprise a hotel, then a village, and eventually a city. A surprising result of our phase 1 and early phase 2 design and test program has been scaling studies that show that a fully integrated megawatt-level Sunflower Power Tower up to 1 kilometer high can be launched into orbit on a single New Glenn rocket and subsequently transported to the moon with its own integrated landing system to enable LPMO. Such a technology provides nearly continuous megawatt-level power where it's needed most on the moon in permanently shadowed regions, obviating the need for nuclear surface power and potentially saving billions of dollars. I'll now turn the presentation to Phil Wall, Transastra's head of engineering, to detail our study results.
As I'm sure all of this audience is well aware, it is highly likely that permanently shaded craters at the lunar poles contain massive amounts of water in solid form. We believe that a critical step to the human future on the moon is the ability to harvest and use this water. This is necessary both as a source of drinking water, a critical part of the moon's infrastructure, as well as an abundant and accessible source of propellant for lunar landers. This makes a mining outpost a key step in near-term lunar exploration efforts, as well as long-term goals to eventually settle and build hotels and cities on the lunar surface. By learning to use the water that already exists on the moon, the number of Earth launches required for lunar and cislunar operations will be reduced by nearly an order of magnitude. These operations will become even more efficient with the addition of cislunar orbiting depots and tankers. The Lunar Polar Outpost mission proposed by Transastra begins with subscale demonstration systems of the Beetle rover and Sunflower Tower delivered on Eclipse-class lander. These systems will demonstrate and validate our regolith mining and power generation technologies. In the following years, full-scale systems will be flown and deployed, starting with a single Sunflower Tower to supply power to the first Beetle rovers and regolith tractors. The outposts will grow over the following decade with increased tower counts to support propellant production and storage, as well as habitats. These habitats will first be home to rotating crews, and will eventually lead way to the first lunar hotels, towns, and eventually cities. We have identified what we believe to be 2 of the critical technologies to enable lunar development on this scale: lunar regolith mining and solar power generation in permanently shaded regions. In the field of regolith mining, we have been developing 2 approaches in parallel, the first of which is radiant gas dynamic mining. With RGD mining, an area of regolith is covered by a rover and heated with a focused beam of microwave or other light waves about half a meter below the lunar surface. This process heats the subsurface and vaporizes volatiles, which are then recaptured as ice using integrated cryo-traps and delivered to propellant processing facilities at the nearest outpost. Our experimental program to test radiant gas dynamic mining is well underway. Experiments have been designed to test lunar regolith mining in Michigan Tech University's Dusty Thermal Vacuum Chamber. In our RGD experiment, the interface of a dome approximately 1 meter in diameter is covered strategically with a pattern of microwave broadside dipole arrays. These dipole arrays are supplied with a high voltage from powerful magnetrons, which allows us to focus up to 6 kilowatts of microwave energy beneath the regolith surface. We have performed vacuum testing on individual dipole arrays in small vacuum chambers of approximately 1 cubic foot in volume. The intention of these experiments was to explore the effects of a low-pressure vacuum environment on our high-voltage system, and to either alleviate or validate initial concerns that arose due to a physical phenomenon known as Paschen's law. At low pressures and without adequate insulation, it becomes more and more likely for plasma breakdown to occur at high voltages, as shown by the Paschen curve. This will result in arcing that can cause significant damage to hardware. As you can see, our initial concerns were validated. Multiple tests performed on a 1.2 kilowatt actively cooled magnetron resulted in significant arcing that caused damage to the dipole arrays. It should be noted that the power concentration in the single dipole array was 5 times higher than it would be in the full array configuration on the dome intended for use in the dusty thermal vacuum chamber. Still, there is significant concern in the ability to safely and reliably insulate a system of this design in high vacuum conditions. While the concept of radiant gas dynamic mining is still being explored, this also gave us good reason to begin development and experimentation on an alternative approach: vessel-based mining. Vessel-based mining uses a very similar approach, reliant on effectively the same hardware and physical concepts as RGD mining. However, vessel-based mining eliminates the concerns of plasma breakdown by excavating and depositing a volume of regolith in a contained vessel, which allows for the environmental conditions to be better controlled. It is within this vessel that the heating and vapor capture takes place, and this also provides the added benefit of using the solid regolith matter for construction purposes. The second enabling technology described in this Phase 2 effort is the sunflower tower. A full-scale sunflower system is capable of delivering megawatts of power to permanently shaded regions in polar craters, using a large thin film reflector payload at the top of the tower. The sunflower design architecture can be optimized from scales in the tens of meters up to kilometers in height. Our Phase 2 work has led to 2 seemingly feasible ways to achieve this, which include tensegrity and inflatable structures, both of which are deployable systems. Significant research and testing has been performed on these tensegrity towers, with geometries and fractal repetition patterns optimized for various scale classes. Transastra engineers have built and tested a lab-scale tower that is capable of being deployed using only motor-controlled actuation. Similarly, we have designed and deployed a near full-scale single tensegrity section of a sunflower tower. In both cases, we have found the greatest challenge of deploying tensegrity towers to be dynamic control of the multiple degrees of freedom required in a tensegrity system. In addition to this work, we have also explored the concept of inflatable towers for lunar applications. Using thin film membranes and very low inflation pressures, we have found that this approach can outperform tensegrity and other proposed deployable solutions with lower complexity and improved reliability. Our team is currently building and testing a series of subscale inflatable towers, gathering quantitative results to experimentally demonstrate the load capabilities of this inflatable tower design.
Thanks for that great summary, Phil. For year 2 of this effort, we plan to further refine our mission studies, showing how LPMO can be built as a commercial enterprise, starting with public-private partnership and then growing to become fully economically self-sustaining. On the hardware front, we plan to complete the build and test program for subscale inflatable sunflower towers, prove our new concept for RGD mining, and plan a flight test program to demonstrate sunflower on the moon about 100 meters tall with multi-kilowatt power output on a Blue Moon cargo lander within 3 years. Now I think we may have some time for Q&A.